This is going to be a talk through of the second MATLAB session where the aim is to load and then plot up one of the transects that we recorded out on the boat. So this shows the latitude, longitude, and then in the coloured scatter plot we've got the temperature in this panel and then the salinity in this panel. This is the overview instructions which we're going to step through, downloading the data and then creating a script to load and recreate this plot, and then we're going to quickly turn that into a function which will then plot each of the 12 transects that we recorded. There is some hints here, and in bold are the different MATLAB functions we're going to use: interp1, scatter, and color map. And we'll be looking at the help files for these as we go. So to start, we've downloaded the data from the DLE, and this is the contents of the zip file that we've downloaded. It contains 24 .mat files, which are MATLAB data files. And there are two types. One is labeled C2D data and the other is labeled GPS data. And then we've got a date, a year, month, day, hour, minute and second for the start time. And so there's a matching file for the GPS data and the C2D data. What I'm going to do just now, so this is the contents of the zip folder, I'm going to create a new folder, and I'll just call that OS105, and I'm going to put the data within that folder, and this is all on my desktop, and so that this folder is going to be the one that's going to contain all of my MATLAB files. It's also going to contain the session 3 files as well. Okay, so I get MATLAB going, and then I'm going to change the working directory to my desktop and to my new folder that I've created, which was OS105. And you can see that I can see the folder that contains the data, and so if it's grey at the moment because I'm not in that folder at the moment, and if I just click on the down arrow here, then I can see the contents of that folder, but I'm still not in that folder. So the data files are grayed out. If I double click on the first one, then it will load it. So that's the C2D data, and you'll see that it's created a variable called C2D data down here in my workspace. And if I scroll down and double click on the GPS data, double click on that, and then I've loaded in this GPS data file, and that then has also loaded in. Now, if you have a quick look at the size of these variables, the C2D data has got 7,423 lines and 8 columns, and the GPS data has got 741 lines and 7 columns. So the first thing we'll do is just figure out which column is which of the data, and so we'll just say C2D data, and then I'll get the first row and all of the columns. And you can see that we've got 8 columns and we've got a big number here, so all of the numbers are multiplied by 10 to the 5 or 10,000, and so we've got the big number here at the start, and then we've got these smaller numbers in the subsequent columns. Now this big number here, which is 7 times 10 to the 5, is actually the MATLAB date time. MATLAB stores dates and times as a single number, which is the number of whole days since the year 0. So this basically tells you that there have been 73,000 days since 1st of January year 0. So this is our date and time, and then we've got a number of other columns. So if we now do C2D data and we do column 2 through to column 8, we can then look at the values of these. That we've got the conductivity, and then the depth, and then the temperature, and then we got 2 voltage readings from external sensors that we didn't have mounted. We've then got the battery voltage, and then the last column is the salinity. So if we're wanting to access the temperature and the salinity, then we need, now this is the 2nd to the 8th column, so although it says 1 here, that's actually column 2, 3, column 4 and column 8. So what I'm quickly going to do is to label these up. So I'm going to say that the C to D time is equal to C to D data and then colon comma 1. So that's the first column, which was this very large number. And then I'm going to say C to D temperature, so I'm going to use big T there, equals C to D data colon comma 4. And then CS is the salinity, equals C to D data colon comma 8. So if we want to do just a quick sanity check on those data that we got the right ones, I can do plot, and then CT is time, comma CT is temperature, and that will then produce a figure. And so you can see that there's variability as we cross various features, and there's a jump in the time. And you can see the numbers here represent time, and I can make them more neat by saying date tick. And that then puts a neater format label on the x-axis. Okay, so this is basically the display that we saw of the temperature record when we were on the boat. The other data set that we've got is the GPS data. So if I do the same, GPS data, and then 1 comma colon, showed me the first line and all the columns. So we can see we've got a big number again. So this is the timestamp, the MATLAB timestamp for this row. So if I then look at 2 to 7, then this shows me the this is actually the date and time information, but then it's these latitude here and longitude here. So the GPS time equals GPS data colon comma 1, and then GPS long for longitude equals GPS data colon comma so that's 2, 3, 4, 5, and GLAT equals GPS data colon comma 6. So again, what I should be able to do is if I close that figure and then I do a new plot, which is G lon for longitude on the x-axis and G lat on the y-axis, I should then have what looks like a believable track with latitude on the y-axis, longitude on the x-axis. Okay, so what we now have are our positions, and we also have our temperatures and salinities, but we need to cross-reference the temperature and salinity at a particular position, and we can see that the C to D was sampling about 10 times faster than the GPS. So there are 700 or so records from the GPS, but there are 7,000 or so records from the C to D. So it's a question of how we go about matching the data up between the two data streams. What we're actually going to do is do what's called an interpolation. An interpolation allows you to do that matching process between two sets of data. If I do a quick plot, so I'm going to close the current plot, and then I'm going to plot the time of the GPS. So I'm going to do plot G time I'm just going to plot it against itself as an example, and I'm going to make these blue crosses. So we should then get a diagonal line which is just showing the time at which each of the GPS readings comes in. If I then hold on and then plot the C to D time in the same way against each other, and if I do red circles, then when we look at the plot, and if we zoom in on this plot, what we'll see when we get close enough let's drag rather than click. Zoom out again. What you can see here are the time of the GPS data points, but then these are the times at which the C to D data points have been recorded. So you can see that they don't quite match up, so we can't just take this point as being the data point that gives us the temperature or the salinity at this actual position. What we need to do is interpolate. So the interpolation basically draws a straight line between the values of the temperature or the salinity at each of these 2 points, and then it picks the value from that straight line at the time that we input or had the GPS data. So to use the interp function, we specify what the output's going to be, which is going to be the GPS temperature is equal to, and then we do interp 1, and then we say the C to D time, the C to D temperature, and then we tell it the times at which we want to get the GPS temperature, so that's the GPS time. And now, when we look at the size of G time and G temperature, they are both the same length. So that means that what I can then do is a plot of latitude, longitude, and then colour it by temperature. To do that, we do a scatter plot, and that has got the longitude as the x values, the latitude as the y values. We then have to give it the area of the circles that we're using. So I'm just going to make up a number and say 10, and then we want to define the colour, and the colour is going to be the temperature of the data points. And there we go. So this is the basic framework of our plot. You can see that we've got a change in colour along our line, and that enables us to look at the spatial pattern of the temperature in this case as we go. So those are the basic elements that we're going to build into a script file, which will then replicate the figure that's given in the instructions. So the reason I've typed these commands into the command window means that I know that they work and I know what the output is, and then I can pull those commands out of the command history and then put them into a script file. So what I'm going to do is type edit, and then I'm going to type plot transect, which is the name of the script that we're going to create. It says it doesn't exist, and so I want to say yes. And this is a new script file that we're going to create. Now, rather than typing in all those commands again, what I can do is go to this command history, and I can then pick out the commands that I know work. So I can take the load commands. If I press the control key on a Windows machine or the command key on a Mac, like I'm doing, then I can load the data. I then am going to give it sensible names, and I'm going to give the CTD data sensible names, so we know that that all worked. I don't need to do those extra plots that we did. And then I'm going to do that inter1 function and then the scatter plot. And then I can copy those and then I can put them into my plot transect script. So we're loading up the data, we're then doing our sensible namings, and then we're doing a scatter plot. I'm just going to tidy this script up. It's very important with a script is if you start it by writing a comment to explain what it is that it does. Plots transact for OS105. So it loads the data, it renames the data that it's loaded into something sensible. It then does the 1D interpolation of the temperature, and what we can then do is copy that line and then edit it so that we've got the salinity. So this is now saying the salinity at the GPS points is the 1D interpolation of the time, CTD time, and the CTD salinity and the GPS time. And then I want to create my plots. So I'm going to do figure to create a new figure window. I'm going to say subplot. Now I want one row, 2 columns, and I'm going to do the first plot. And then I've got a scatter plot, which is the temperature. And then I'm going to do a subplot, 1, 2, 2, which is second. And then I'll say scatter glon glat size 10 for those data points, and then I'll say gs. Now there are extra bells and whistles we can add to the plot. We can do xlabel, which is longitude in degrees, and ylabel, which is latitude in degrees. I'll copy these down to the next plot. I'm also going to add a color bar. And then we will save that. Then we'll go back to my window here. Now, just take note, I'm in the OS105 folder, and that has this OS105 data 2017 folder within it, and then I've got my script file called plot transact. Now, if I do clear all and then close all, I've cleared my workspace, I've got no figures, and if I then type plot transact, what I did there was I typed the first part of the word and then press the tab key, and that completes it. What it should do is then load up the data, and then it will plot it. Now, this is useful. You can see that I've got an error message has come up, and it says undefined functional variable color bar, and then it's on line 27 of plot transact. So if I click on that line 27, it takes me to my script, and you can see that I've got a typo here because color bar doesn't exist. What I wanted was color bar. If I save that, if I then run the function again, I press the up arrow, press enter, then you get your plot. Okay, so if we then compare that plot to the one given in the example, you can see that we need to add titles, and we need to add a grid, we need to add a box which completes the axes, and we need to fill the dots, and we need to change the color maps so that we've got different colors for each of these subplots. So I'll take you through each of those components in turn. So we'll go back to MATLAB, and then we'll go back to our script file. So we needed to add a title, and this one is temperature, and that is degrees C. We can then copy that and paste it down here, and the next one is salinity in practical salinity units. We then need to add a grid, so we say grid on in both of the subplots, and if we say box on, that then makes a nice border all the way around the axes. So I'm going to run this. So if we do plot transact, we are getting there with our plots. Next thing I'm going to do is to fill in the dots and maybe make them a bit bigger. So to make them bigger, I change this, which is the area of each of the dots. It's just a number that defines the area. If I double the size of them, that will make the area bigger. And I also needed to fill them in. So how do I fill them in? I can't remember off the top of my head, so I'm going to do doc scatter, which will then load up the help system, and it will tell me hopefully what I need to know. And you can see that if I put the word filled in, if I read further down here, it fills the circles. So that's what I want to do. So at the end of my scatter, I say filled, and then I can copy that and then paste it down here. Go back to my command window, run the plot transact again, and we are just about there with our plot. And the final part is to change the colors of this plot so that they are different to the colors of this plot. Now you can choose the colors using the color map command. So if I read up the help for color map, then this allows you to change the color map of one particular set of axes. So I can, if I say which axes I want to change color map of, then what I can do is then choose what are the colors that are actually used to define the values. If I scroll down, you can see there's all sorts of different color maps that are available. You can make your own color map. The default one is called Perula, but a useful one for temperature is called Jet, because cold values can then appear blue and then warm values can appear red. Perula is quite nice for salinity, perhaps, but you can choose other color maps depending on what you think most clearly displays your data. So we're going to stick with this Perula color map for the salinity, but we'll use Jet for the temperature. So to do that, I'll go back to my script. Now, I need to give a name to each of these axes. So I need to say subplot 1 equals, and then I'm going to put a semicolon at the end of that, and then I'm going to say subplot 2 equals. And what this enables me to do is to give a name to this axis that the subplot command has created. And then when I set the color map, I can say color map, and I want to set the color map of subplot 1, and then I'm going to set it to Jet, and then in this case I can set the color map of subplot 2 and I'm going to call it Perula. I'll save that and then I can go back here and then run my plot transect, and in this case you can see that it's now updated the color map of my temperature, and it's stuck with the default on the salinity. Now you can choose what color maps you like, you can choose the dot sizes that you want, and you can also change the ranges of the colors and the salinities. I'll just show you how you can change those. So we can, if for example we wanted to go from 9.1 to 9.5, so increase the color range just slightly. I'm just going to close all my old plots. Then in my script I can say set GCA, which is the current axes, get current axes, and then I can say CLim. Previously we set the X lim and the Y lim. In this case we're setting CLim, which is the color limits, and then I can say go from 9.1 to 9.5 on the temperature. If I save that and go back here to plot transect, you can see that we've now defined the color limits that we're using. So that means that for all of the figures that we plot, you could have the same color limits if that's useful for comparing the change in the temperature or the salinity between plots. Okay, so we're basically there with producing one set of plots. I'm quickly going to show you how to turn that into a function which we can then use to quickly plot up any of the data sets. So to turn a script into a function, we start by using the keyword function, and then we give it the name, which is plot transect, which is just the name of the file that we've got, and then we are going to give it a piece of information. So a function is basically a closed box of commands that you give information to, and then it operates on that information and produces you an output. And the output can either be something that is displayed on the command line, or it can be a plot. Now the information that we're going to give it is basically just the number of the transect that we want it to plot. So I'm going to call that trans no, which is the number of the transect from 1 to 12 that I want it to actually plot. And it's again useful if you just add an extra comment explaining how you actually use this. So input trans no to define which transect from 1 to 12 is to be plotted. Okay. The next question is how do we take a number from 1 to 12 and turn that into a file name? Well, to do that, what we need to do is to create a listing of the data folder. So the data folder is this OS105 data folder. So if I erase those two lines which just loaded one particular data file, what I'm then going to do is to do a directory listing. So I'm going to say that D, which is the directory listing of the, let's label it, we'll be consistent with what we've done before. So the C to D directory listing okay, so what I'm going to do is do a create a list of the file names of the CTD data. So I'm going to call that list CF, and then I'm going to use the command dir, and dir creates a list of the folders within a list of the files and folders within a directory, and I'm going to then say dir, and I need to give it the name of the folder that contains the data. So that's OS105 Data 2017. Okay, so it's going to look in that folder, and I want it to look for all of the data that begins with the word CTD in this case. So you can see the CTD data starts CTD data. So I'm going to look for anything that begins CTD data, and then I use the wildcard, which is an asterisk, which means look for any file that begins CTD data. Now, the way that I need to put this together, this directory listing, is to group the file name, the folder name, as well as the file name that I'm looking for in with what's called the file separator. Now, a file separator is basically what separates out the file name from folder names. So if I go back on my command history and show you the load commands that we've used, you can see that when you do a load command, you've got a /, which is in between the file name and the folder name. And this / is a file separator. Now, on a Mac, it's a /, but on a Windows machine, it's a \. And so to write code that can work on either a Mac or on a Windows machine, instead of writing the forward or the \, you write this keyword file sep, and that then it gives it the correct one. MATLAB decides on the correct one. So what this is saying is that do a directory listing of this folder with the correct file separator and then the CTD data files. We'll then do a GPS file listing equals dir, and then we'll just copy what we've written above, but I'm going to turn that into GPS data. Okay, so I've got my data. The next list of data file names. The next thing I want to do is to load up the ones that correspond to the transect number. So to do that, I can issue a load command, and then I can say CF, and then I can say the transect number. So if it's number 1, so that would be the first file on the list of the CTD data files dot name. So that gives me the name of that data file. Now this on its own isn't actually going to work, because what it's expecting is this folder name and then the file separator before it. So if I copy that from there and put it in here, and then complete that with a square bracket, that will then load my first CTD data file, and then I can copy that and then paste it, and we'll load up. If we said give us the first file, it will then load up the first GPS data file as well. Okay, so what we've now done is, if I save that, we've created a function now that creates a list of the files in this data folder, and then it loads the file corresponding to the number that we've given, and then it creates a plot to do that. Now, there are different ways that we can do it, but what we could do is, if we say create a plot that is numbered the same as the transect number, so we'll create a new figure window for each plot that we've got. Now I don't want to run this command, so I press Ctrl and C just to skip to the next line without running the command. If I do close all and clear all, then I'm going to run this plot transect command. Now if I run it on its own, because I've turned it from a script into a function, I'm going to get an error message which says not enough input arguments. And an input argument is basically this information that you need to pass into the function to make it run. So right now, when I run it like this, I haven't told it which data file I want it to run on. So I need to put in brackets, I want the first data files to be loaded up. So what it then does is it's gone into the data folder, it's created a file listing of all the CTD data files and all the GPS data files. It's read the first one of those, and then it has plotted that data. So that means that figure 1 is the first transect. If I want to open up the second pair of data files, we then run into a new problem which we need to fix. Okay, so what's happened here? Now with error files, error messages, we read them from the bottom up. So you can see there's an error in plot transect line 18 at this interp1 function, and it's on the, what it doesn't like is that if we read further up, the coordinates, the input points must be finite values, nans are not permitted. Okay, so it's likely that if we look in the second data file, which is what we've loaded up, either the CTD data or the GPS data, that we have a nan within that data. So that's the GPS data. If I double click, load the CTD data. And if I want to find where nans are null values, so I can say tell me the sum of isnan of CTD data. Okay, so what's this saying? Isnan is a function which basically, if you've got a matrix of data, some of which are not a number values, then it will put a 1 where the not numbers are and a 0 where they're not. So if you then add that up, it will add up each column and tell me how many nans there are in each column. So what this is saying is that in that CTD data, every single column has got 1 nan in it. If I then do the same for the GPS data, you can see that the columns that we're interested in have no nans in it, and then there's one column which is made up entirely of nans, and that's because that was going to be a depth reading that the GPS, if it had an echo sounder attached to it, would have been giving. So the problem that we've got is actually in the CTD data. So now if I look at the CTD data, I'll look at the first row. Okay, the first row is all nans, but when I go on to the second row, then it turns into proper values. So what we're now going to do is we're going to look and find a row that has got a nan in its first value, and then we're going to strip out and remove that row, and we'll do that immediately after we've loaded up the CTD data. So we'll do our loading, and then we're going to say CTD data, and I'm going to find, so I'm going to say isnan of CTD data : 1. So I'm going to use the first column, and I'm going to say, so that will then give me basically the first row. So I've looked in the first column for all the nans, and it will then tell me which rows have got nans in. And then I'm going to say all the columns, and then I'm going to say equals, and then if I do empty square brackets, and what that does is it basically deletes those elements that have got a nan will delete all of the columns in every row that has got a nan in that first column. So if I save that and then I go back to my plot transect command, then you can see that figure 2 now plots. So this is transect 2. If I do transect 3, then that goes on and so on. Now you can see that the color range is not working properly from the ones that I define myself. So I'm going to actually just remove that set GCA line. I'll comment it out, which means I put the % symbol at the start, so it's then ignored, so that I can then plot all the transects to have a look at the actual range of values that are included. And then I could go back and then replot them using a fixed set of values if that's what I wanted. Okay, so that's it for this session. We've created our plots and we've turned it into a function which enables us to quickly look at each of the transects in turn, and we've used interpolation to match the sampling location to the C2D data that was collected nearest to that data point.